Very good morning, very good evening to ladies and gentlemen. It is with great, great pleasure that I welcome you to this Geotechnical Forum organized by the Sri Lankan Geotechnical Society. In the Geotechnical Forum today, we have Prof. Thilakasiri talking to you on optimization of the design of rock-socketed board and cast in-situ piles. Professor Thilakasiri is the current Dean at the Faculty of Engineering of Sri Lanka Institute of Information Technology, SLIT, and he is a professor attached to the Civil Engineering Department of that institution. He obtained his first class honors in Civil Engineering from the University of Moratuwa and proceeded to do a master's degree at Imperial College Langton. He completed that with distinction and obtained a PhD subsequently from University of South Florida, USA. And he has served as an academic at various capacities since 1999. In parallel with his academic career, he practiced as a senior level engineer in many national level projects, obtaining the charter from the ISL and became a fellow of the ISL in year 2007. Further, he engaged himself as a geotechnical consultant to some projects in foreign countries as well. Apart from this experience, he has gained through engagement Sri Lanka. He has obtained valuable experience from major educational institutes in USA, UK, and Australia as a research student, adjunct faculty, and as a research fellow. Before becoming the Dean Faculty of Engineering at SLIT, he was involved in academic administration by serving as the Director of Undergraduate Studies of the Faculty of Engineering and the Postgraduate Research Coordinator and Professor in the Department of Civil Engineering, University of Moratuwa. So with that introduction, I invite Professor Thilakasiri to start his presentation. Over to you, Saman. Thank you.
Thank you, Professor Thilaka. You can hear me, right? Can you? Can you hear me?
I can hear you. I can hear you.
Okay. Thank you for the nice introduction. So today, the topic is optimization of the design of rock-socketed board and cast in-situ piles in Sri Lanka. So my presentation would be like initially based on the theoretical concepts. So on soil and rock at both, and then later I will talk about the rock bearing capacities, right, which we are not covering in Sri Lanka at the moment. And then there will be few case studies, right? Two case studies. One is on soils, that is the measured capacities in soils, and then another one is on rocks. So that is the format of my presentation. So initially, to lay the introduction, to lay the foundation for the discussion. So I will talk about the vertical loaded piles, right? So here, when we talk about the piles, we have board piles as well as driven piles. So we will consider here only board piles, because those are the only rock-socketed piles in Sri Lanka. So when we consider the capacity of piles, so we can consider both the structural and the geotechnical capacity. So here we'll talk about the geotechnical capacity only. The structural capacity will be discussed next time, most probably when we discuss about the pile load testing. So when we consider the design approaches, so we have basically the resistance factor design method, that is basically based on the limit state design, and permissible stress design. So that is basically we have a factor of safety, and then we divide the mobilized capacity, ultimate capacity, with the factor of safety, and then use that as the allowable capacity. So that is the method that we generally use in Sri Lanka, right? So we are following earlier, actually we follow BS 8.4. So in 2015 also they have a new version. So that version of BS 8.0.4 talks about the Eurocode 7, right? So the based on the Eurocode 7, that will follow the limit state design or the even for the geotechnical design, right? So when if you want to do the Eurocode design, limit state design, then the load should be given as the according to the code, and then we can use 3 design approaches in the Eurocode according to the Eurocode, and then we can check our piles. So in my opinion, so we can optimize the piles, right? The design of the piles using the design approaches as well. So right now we are using the permissible design approach. So if you move on to the limit state approach, then we may be able to optimize that. So that is for a different discussion. So we are not going to discuss about the design approaches here. So we will discuss how to measure the capacity, how to estimate the capacity and measure capacities later on. So we can use that for the permissible design as well as for the limit state design. So we will not basically limit ourselves to the discussion on the design approaches. So that is for another day, and we will discuss only about the method of estimation of the capacities. So there are actually a few thoughts, of course, few schools of thought. So in that case, so some people say that the capacity can be estimated using the skin friction and end bearing. So some people say it is a combination. So you cannot talk about the skin friction and end bearing, right, separately. So because one is another depending on the other one. So here what we do is we will stick to the skin friction and bearing capacities of the piles and determine. So how we can determine the skin friction in the piles for soils, and then skin friction in the rocks, and then skin friction in end bearing in soils and end bearing in rocks. So that is our discussion. Now when we talk about the design approaches, design methods, right? So the design methods actually mainly have capacity estimation methods. We can say static methods and dynamic methods. So we will discuss only about the static methods here, right? So basically we will talk about the strength parameters, how we can use the strength parameters of soil and rock, and then what are the empirical correlation related to in-situ testing that we can get the capacities, right? So those are the limits of our discussion. So we will not talk about the dynamic methods here in this discussion. So later on in the presentation, I will actually look at the case studies, right, using the static load testing, right, mainly using the instrumented pile load testing results obtained in Sri Lanka. So if you talk about the soil medium, right, so we have the skin friction in soil medium, right? So you are familiar with this particular concept. So we have the elements, pile element and soil element. So we have the skin friction mobilized at the interface, right? So this the skin friction that we mobilize will actually increase linearly with the displacement of the pile, and then it will remain constant. So we will see later how we can whether it will follow this particular pattern when we actually measure the skin friction and bearing later on in the discussion. So when we talk about the skin friction, of course, generally the normal stress against the pile, right? So the pile will be pushed against the normal stress. So the skin friction will have two components, that is the frictional component and the the cohesive component, right? So we say the addition, that is CA, and then this is the frictional component that you are familiar with, right? So normal stress multiplied by the friction angle, that is. So in our case, actually we know that in soil mechanics we will say that the ratio between the horizontal stress and vertical stress is a Ks. In this case, I'm sorry that you cannot see that, but it is a Ks value, the ratio. So if I replace this sigma in with case sigma v, then we will get this particular equation, right? So this is the general equation that we will be using in the estimation of skin friction in soil media, right? So when you talk about the total carrying capacity, so this will be in kilopascal, right? So when you talk about the total carrying capacity, you have to integrate from total length of the pile multiplied by the perimeter length of the pile, and then so this is the final equation to calculate the total skin friction capacity of the pile, right? So this will have actually the cohesive adhesion component and the frictional component, right? So that is the format of that particular equation. So now we will consider clay and sand separately. So in clay soil, we know that generally under undrained condition, phi is equal to 0. So that part of the equation, that is this part of the equation will go out, right? So what we are left with actually the adhesion component, right? So that additional component is equal to alpha times the undrained cohesion, right? So that we determine that. So there are many correlations that were developed by the different researchers, but I will stick here with the method that is actually to determine the alpha value, right? That is the coefficient alpha value, alpha times Cu is the skin friction. So the alpha value will be determined by the I'm sorry, it is not here. It is actually based on the curve developed in the Bold's textbook, right? So that is the relationship between the skin friction, ultimate skin friction, and the cohesion value, basically the shear strength value, right? So that is the relationship that we'll be using in this particular case. Now, when it comes to sandy soil, that we know that for sandy soils, generally the cohesion component is quite small or maybe 0. So in that case, we are left with only this part, that is sigma v Ks tan alpha phi a. So that is the frictional resistance or the skin friction resistance. So now there are two components here, right? One is what is the variation of sigma v very close to the pile, because the skin friction will happen very close to the pile. So what is the variation of that sigma v? And then the other one is what is the variation of this Ks value, right? So how the Ks will vary, because as we know that there are different methods of pile installations, right? So depending on the method of installation, this Ks can vary. For example, if it is a board pile, then what you do is actually we drill a hole and then fill that with concrete. So that is different when it comes to a driven pile. So in that case, we will actually insert the foreign object into the medium. So we are actually moving aside the material which is already there. So therefore, this Ks value will depend on the type of the pile. So these curves, right? So there are actually generally if you look at the results of the field load testing, we can see that the skin friction, the skin friction value will actually vary and then will come to a constant value. So that is, it will vary linearly and will come to a constant value. So that cannot be explained using, say, if the sigma v varies linearly with the depth, right? So generally that is the case, but that cannot be explained using that particular theory. So what we do is we assume that the very close to the pile, the vertical effective stress will vary as it is up to a critical depth, and below the critical depth it will remain constant. So that is the generally the critical depth concept that we use, because it is based on the sum of the load test results, right? So that are measured results, and so up to a particular level it will increase linearly and thereafter it will remain constant. So that is the critical depth concept, right? That is a variation of sigma b very close to the pile, right? So away from the pile, little away from the pile, it will be a normal variation of increase with the depth. But very close to the pile, it will vary according to that concept. That is, it will vary according up to a critical depth, and then below that it will remain constant. So if you look at the Poulos and Davis textbook, right? So they give this particular curve to determine the critical depth versus diameter ratio, right? So you can see that it depends on the phi value, phi of the surrounding medium, surrounding soil, and depending on the phi value, you can determine what would be the critical depth and the diameter ratio, right? So, and then the Ks value will depend on this also again obtained from Poulos and Davis, right? So you can see for driven piles, the Ks value for a given value of phi, Ks value is increased, a higher value, because of the method of installation. But both piles, the Ks values are still smaller, right? So that is basically what is proposed in Poulos and Davis textbook, and it can be actually we can according to our arguments, right? So that may be correct. But what we say is that for driven piles, like if you have a phi 1 value before the installation of the pile, then you have to modify the phi value according to this equation for the driven piles, and for both piles always initial phi value minus 3 degrees will give you the installation phi value after the installation of the pile. So you have to use those values in this particular chart and determine the Ks value and the ZC over D ratio. So that is the skin friction, how you can determine the skin friction. Of course, there are many methods, but what I have explained is basically the methods that are commonly used, right? So if you look at the end bearing, right? So the end bearing estimation method. So what is used is actually, now say if you look at a pile like this, right? So you look at a pile like this. So the end of the pile is actually resting, acting like a small, shallow foundation. So the effective zone of that particular so this will be actually a local failure, not this failure line will not come to the ground surface because of the depth, and so it will be actually failure surface like this. So in this case, we say that the effective height above the base is about 6 to 10 times the pile width, and below the pile width it is 2 to 4 times. So on average, we say that it is 8 times B above the toe of the pile, and 3 times B below the toe of the pile. So that is the effective area. So you have to estimate these bearing capacity factors in this effective zone, right? So these are the bearing capacity factors, and you are familiar with this equation. So this is the shallow foundation equation. So this bottom of the pile will act like a shallow foundation, and there will be local failure. So depending on the failure surface, failure shape of the failure region, so you will have to get the NC, NQ, and N gamma. So these are the factors that we consider, and generally this N gamma factor it's multiplied by the width of the pile, and it is generally smaller, right? So we disregard that term, the third term of the equation, and we consider addition of these two will give the ultimate end bearing capacity, right? So we have determined NC and NQ, and generally the NC is obtained from this particular curve that is developed from the Skempton in 1951, and you can see that after a while, right? So this axis here in this particular graph is L over B ratio, L over BR in case of the pile group, but since we are talking about a single pile, it is L over B ratio, right? So after L over B ratio is 4, this NC value is actually for a circular or square footing, it will be constant. So it is about 9. So that's why we generally say NC value is equal to 9, because for piles, L over B ratio is greater than 4, right? And for a strip foundation, of course, this is this will be asymptote. The asymptotic value would be about 7.5, right? That is the generally we are using the 9 value, 9 times CU, because in our case most of the piles are circular or square. And n gamma value you can obtain from this particular chart, right, which is there in the Poulos and Davis textbook. And even here you have to actually modify your 5 values, right? So these are the 5 values before installation of the pile, and these are the 5 values that will be used. The 5.1 is the before the installation, and the 5 value is the after installation. So this value 5 value you have to use this in this particular chart. For driven piles, the 5 value is increased up to 5 value is equal to 40, but below that, if it is above 5 value, above 40, it will decrease, right? But both piles always the after installation, the initial 5 value will decrease, right? So you have to use those the modified 5 values in your calculation. So there are empirical correlations now. So the most commonly used empirical correlation is developed by Mayhoffs in 1956, 1976. And so it says the ultimate skin friction is a factor times N55. N55 is the actually statistical average of the blow count, of the SPD blow count in that particular strata, right? So, and this factor is depending on is 2 for large volume displacement piles. So take my words, large volume displacement pile is actually driven piles, right? So in driven precast piles, so the factor is equal to 2. And for small volume displacement piles or replacement piles, right, we say this factor is equal to 1. But if you look at the ICTAD guidelines, right, so CEDA guidelines, right, nowadays people call it. So if you look at CEDA guidelines, so it says this the factor is equal to about 1.3. So that is for the both piles, right? So we will see later how the measurements will tally the values given there. So values given in the CEDA guidelines. Now the other correlations to generally widely used correlations for determination of N bearing is actually again proposed by Mayhoff, right? So it says the 40 times N, right? N is the SPD N value, and 40 times N LB over B ratio. That is, LB is the length in the bearing strata divided by the width of the pile, right? So here what you have to understand is that now you have to get the average SPD N value, right? So it says average SPD N value in the influence zone, right? So earlier I mentioned that the influence zone is about 8 times B above the pile toe, and 3 times B below the pile toe, right? So you have to get the average SPD N value in that zone to determine this particular equation, right? So the original equation proposed by Mayhoff, right? So later on, actually, ICTAD guidelines or CEDA guidelines, they change it. So L over B ratio, right? LB over B ratio, they assume it as 1, right? And say that N bearing capacity is 40 times N, right? So 40 times N, and so obviously this value should be less than 380 N value, right? So in the ICTA guidelines or CEDA guidelines, it is assumed as 1, right? So that's how we get the value of 1. So that is the empirical correlation we are using, and we will see later how that will actually relate to the measurements. And other one is actually correlations with the cone penetration test data. So the N bearing capacity is equal to the QC value. That is QC is a cone resistance value. So there again, you have to get the average value within that influence zone or for the toe or the pile N. So those are the methods that can be used to estimate the skin friction of piles and the N bearing of piles, right? So now when we come to go to the bedrock, right? So bedrock, you have determined because generally in Sri Lanka, most of the piles we find our bedrock in about even 20 meters, or on average 20 meters. In some places it can be found at very shallow depths, and in some places at deeper depth because of the weather, right? So because of that, we separate most of our piles to the bedrock. So it is very important that how you can estimate the skin friction offered by the rock socketed region and the end bearing offered by the socketed region or the bedrock, right? So we are not talking about the coarse stones here, right? That is, those are boulders that are found in the subsurface, but we are talking about the bedrock, that is the constant bedrock that we find. And generally, if you want to confirm that through investigations, you have to drill about 3 times minimum into the bedrock and show that it is all bedrock that you find, right, in those 3 meters. So now first we'll talk about the skin friction, ultimate skin friction. So this is the method proposed by William et al. So if you look at the CEDA new guidelines, that is there, right? So so it says alpha, beta, and sigma c, the values, right? That is those are the equations. That is to determine the ultimate skin friction. You multiply alpha, beta by the sigma c is the uniaxial compressive strength of the rock that we are talking about, right? So so these are the curves that you can obtain the alpha value, right? And beta value you can obtain from this particular the curve, right? So it depends on the mass factor, and this one is actually alpha value can be obtained from the unconfined compressive strength. So depending on the curve that you consider, you can obtain the alpha value directly. But here the beta value, you have to determine the mass factor, that mass factor J, right? So how you can estimate the mass factor J is actually using this particular relationship, right? So they have given this particular chart. So depending on the RQD, you can obtain RQD, you can obtain the mass factor, and then you can obtain the J value from this particular, these are the values given, and then use those J values in this particular equation in this particular chart to determine the beta value, right? So you can determine this alpha, beta, and sigma c, and the alpha, beta, and sigma c, then you can determine the ultimate skin friction. But at the same time, if you look at the ICTAD guidelines or CEDA guidelines, so it will say that there are 2 methods of estimation. One is the Williams method, right? So this method that is given in the ICTAD guidelines. And but if you look at the other one, it says maximum you can assume is about 200 kilopascal. So that is so either of these two you can use the skin friction estimation method. But now if you look at the even the Williams method, right? So later, it is found that if you look at the other textbooks like Tomlinson, it says that Wiley he found that only the estimated value, 25% of the estimated value is mobilized if you use bentonite slurry in the rock socket, right? So if you use a normal case, right? Normal situation, like if you assume RQD is at 50, then the strength ratio is equal to strength uniaxial compressive strength is about 10 megapascal. Then so you can get the bearing capacity in the range of around 845, but the mobilized value would be 210 because we are using the bentonite slurry to drill the rock socket. So therefore, if you use that particular the 200 1/4 value in the equations, then generally 200 value mentioned in the CEDA guidelines or the ICTA guidelines is correct, right? Or maybe come closer to that. But later we found that actually when we did the instrumented pile load test, right? So instrument pile load test through the instrument pile load test, we can actually measure the mobilized capacity, right? So if you measure the mobilized capacity, we found that there's no effect of the bentonite slurry, right? And so it is evident from the results that there's no effect of the bentonite slurry. So you don't have to mobilize, based on the limited number of tests, of course. But with more and more tests, we can actually increase the skin friction capacity, and maybe we can later on increase the limit. And I will show you later. Measured results, the skin friction results are actually supporting that increment later on, right? So we will see that. So this the skin friction from the other one is actually Hong Kong guidelines. In Hong Kong, it is actually bedrock is quite similar to granitic and igneous formations in Sri Lanka, but of course it is a little harder than that. So we don't get that much weathering there. But so they have done the measurements, right? So based on that, they have prepared what is called Hong Kong guidelines for the pile design, right? So according to these guidelines, you can see that now they are proposing the skin friction as 0.2 times the unconfined compressive strength to the power 0.5, right? So that is the relationship that they propose based on some limited number of test results. Because now even here you can see that most of the the measured values are actually not loaded up to the failure, not fully mobilized, right? So even in that, you can see that the skin friction values they are proposing, right? So easily you can get in our rock, the unconfined compressive strength is about more than 10 megapascal. So you can even 10 megapascal, we give a value of about 700 or 600 kilopascal. That is the the skin friction value that is mobilized in the rock socket, right? Based on the Hong Kong guidelines. But when it comes to the end bearing values, right? So if you look at this particular chart, right? So that is given in the CEDAW ICTAD guidelines. Actually, now this is the chart that is used most probably by most of the engineers in Sri Lanka. And so I am thinking that I am not criticizing the use of this particular chart, right? So then with the limited number of test results, and we should have used something to estimate the end bearing capacity, allowable. So what is given here is actually allowable bearing pressures, right? So now if you look at this value, this chart, so there are a few problems here. One is that this chart on this axis, right? What is called is actually RQD, or the fracture spacing, right? So now if you look at the RQD value here, right? So the value given here is about 75%, right? So if it is less than 75%, you have to the fracture spacing is actually less than about 200 millimeters, right? So the curve is given only up to about 125. So it's about, I think, 50 RQD. So if the RQD is less than 50%, right? So you cannot use this particular chart. So that is one disadvantage, right? So even if you consider like 20 megapascal capacity here, the uniaxial capacity, right? So the allowable capacity about, if the rock is about 75% RQD, you get a capacity of about 5 megapascal, right? So it is slightly in the lower side. So maybe that is due to the fact that this was obtained from this was obtained from a curve, right? Curves that were developed for a different purpose, right? If you look at this one, right? For example, now I have taken here these 4 curves, 4 rock groups, right? So they have used actually rock group 2, right, to this particular to develop this particular chart, right? So this was developed. If you look at this here at the bottom, it says allowable bearing pressure for square pad or square pad foundations, right? So this is for a, this was developed for a, developed for a pad foundation, which is actually socketed to the bedrock, right? So if you look at that and what is given in the BS 8 note 4 in of course, in 1986 version. So this is a fairly old version at that time when we developed this curve, right? So it says this is an approximate method, right? And if you want to get a conservative results, you can use this. So maybe very reasonable that we use that at that time, because we did not have the results to back it up. But with the more and more results coming, we can actually modify this. We can modify this and optimize and increase our capacities of the end bearing capacity, allowable end bearing capacities. So I am just speculating, but of course, we have to have some test results to back that claim. So this is the method that we use to obtain the end bearing capacity. The other problem is that we are actually, if you look at this chart carefully, it will say the UCS on this axis, that is uniaxial compressive strength, and the RQD. So it will depend on two parameters, right? So uniaxial compressive strength and the RQD or the rock, right? So depending on those two parameters, only we determine the allowable end bearing capacity. Now, if you look at this these two cases, right? So what I am going to show here, right? So in this particular rock core, right? So you obtain the UCS value of 58.23. That is the UCS value obtained, and corresponding to that, the core box give these test the rock cores. And if you look at it, these are very solid rock core, and you can see that there's no weathering of the interfaces, right? So, and the core recovery is about 98%. Of course, due to fracturing, you get about 20% of RQD, right? But if you test the this particular rock in uniaxial compressive strength, you obtain 58.23, right? So that is case 1. And if you do this, the case 2, here also, like you obtain this particular rock from 21.05 to 22.055. That is this particular rock core, right? So here also, if you determine the of course you can do the UCS test on this one, right? So when you do the uniaxial compressive strength, what you do is actually you will get a rock core, right? So which is actually left behind by the circulation of the fluid during the coring of the for the piles, right? So if you test that, right? So this is actually not for the pile coring, this is for the investigation, right? So if you test this one, this solid rock core, still of course using the empirical correlations, you can obtain about 56.76 of the UCS value, estimated value. But if you want, you could have actually tested this value. Of course, here it is slightly lower, right? You can see that this particular profile here gives actually low core recovery values, right? But the UCS values here are fairly high. So can you compare the original value, the earlier value, this value, right? This rock, right? And you get a UCS value of 58.23 with this one, right? So you can see here, this is actually weathered particles. There are weathered particles, right? And so what you obtain is actually UCS is what is left behind after investigation, after coring, right? So you determine the allowable capacity, right, based on the UCS and the RQD, right? So whether that is the use of the UCS is reasonable, that I have a question here. because now most of the material between the in the void spaces have been actually washed away, right? So what is left behind, we are obtaining the strength, right? Of course, you are using the RQD value, right? That is true, but use of this UCS alone is that we have to look at again. So that is a another disadvantage of using that particular chart. Now, so based on this, right? So if you are using the Hong Kong guidelines, right? So the Hong Kong guidelines, they determine based on the some testing done. Say they say that the end bearing capacity, allowable end bearing capacity, can be much higher, right, from the testing. And so what they find is actually that value can be related to the rock mass rating. What is a parameter called rock mass rating, right? So I will describe that rock mass, how to determine the rock mass rating later, right? So that is how they found what they find out, right? So their allowable end bearing capacity can be higher than, right? It is related to the rock mass rating, right? So now to back that up, so let me show that so these are the test results they are showing, right? So the test result they are showing here is now on this axis is rock mass rating, right? So this axis is allowable in bearing capacity. They are recommended, right? So these are actually the test results. What is shown here are the test results. You can see that now none of the test results, actually only 2 of them have actually mobilized up to a certain capacity, right, of the end bearing, right? But most of the tests will show fairly have not reached the even 1% of the pile diameter settlement, right? So these are the test results, right? So these are the one they are proposing, right? So depending on the RMR, right, what is the allowable in bearing capacity that they are proposing, right? So now what we actually determined earlier was something like 5 megapascal capacity from the other chart, that is relevant to about 50 RMR 50, right? So I will tell you how you can determine the RMR later, right? Or of course, now that I will say how you can determine the RMR, right? So they determine the RMR based on this chart, right? So if you look at this particular chart, right? So this was developed originally by Benny Wasky, right? So in 1989. So that was, there are a lot of charts developed afterwards, but they use only this particular chart, right? So the maximum, RMR that you can get from this one is about 86, right? So 86 is the maximum RMR you can get, right, from this particular chart. Now, so this chart, if you look at it, so it will have actually, it will consider the intact rock pieces through the what you call the uniaxial compressive strength, and also the RQD value. So that is the intact, amount intact rock that are left behind after the drilling process, right? And then it will consider the fracture spacing of these fractures, right? And also more importantly, what is inside the fractures. It will see, like, you can actually, RMR will depend on what is the inside status, inside material of these fractures, right? So what is the fracture surface, and what is the whether the material inside the fractures are hard, right? So if the rock pieces are weathered. So these are the things that we'll look at when you determine the RMR. So you can determine the RMR using this particular chart, right? So if you look at, so this is the first one, right? First 2 factors based on the intact rock specimen. Basically now here you determine the UCS and the RQD, right? And then the next one is actually what is the fracture spacing. So this is actually, I have shown here the rock core obtained, right? That is from the coring of the rock. So you can see that these are the fractures. The yellow colors are fractures, right? Of course, I have assumed here that fractures are infilled with some material, but it may not be the case, right? So what is the spacing of these fractures, right? So that is that is actually given a rating here, right? So that is the first one is the UCS and the RQD. So those are given the ratings, and then the spacing of the fractures is given a rating, and then finally basically condition of the joints or the fractures, right? So what is inside these fractures? So they will be determined from these the ratings, right? So there are actually 4 ratings here, right? So depending on the separation of the fractures, depending on the roughness of the fracture surface, and the infill material, right, and the weathered state of the surface here, rock surface here, right? So you can you can determine the RMR. So if you want to determine the RMR, it is the summation of these factors. You can determine the RMR, right? So what they say is basically this is better than just considering the UCS and the RQD that were considered here, but more than that, right? So we can envisage that the fracture spacing and what is inside the fractures will also determine what is the capacity. So using the RMR is more justifiable in our in engineering sense to use in the estimation of the allowable and bearing capacity. So they are proposing this relationship, and they have actually proposed in this if it is less than RMR 40, right? So you can get the ultimate allowable capacity and bearing capacity of 300, 3,000, and if it is 50, so it is 5,000, and if it is 70, you get 10,000, and if it is 88, that is you can get 14.5. 14,500 allowable in bearing capacity. So that is it depends on the RMR value, right? So those are the methods that we can use to determine the skin friction in soils and end bearing in soils, and skin friction in the bedrock and the end bearing in the bedrock. So those are the method that we can think of. Of course you can mention the other methods as well, but those are the common use methods, right? So now first we look at the case studies, right, involving the soils, right? So this particular piles, right? So there are actually 3 locations, right? So these actually 3 board pile locations. All of them were subjected to instrumental pile load testing, right? So then in this any of these piles actually 3 strain gauges were installed. So if you look at the instrumental pile load testing, right? So between strain gauges you can measure the skin friction. So I am not going to go into the theory of doing that, but you can determine the skin friction, right? So if you have the another strain gauge at the end, you can determine the end bearing, the mobilized one. Mobilized means so what is what is there when we apply the loading, right? So in this each of these piles actually 3 strain gauges were installed, right? And at these 3 locations they have done actually the borehole testing, right? So the SPT at these 3 locations within the reasonable depth, right? So what we do is actually we will compare, right, with the measurements with the estimation methods, right, for both skin friction and end bearing. So all these piles are actually within the soil, not supported to the bedrock, so we can determine the skin friction in soils and end bearing in soils, mobilized ones, right? So now in the estimation of the skin friction, we use actually method 1 is use the empirical correlation proposed by Mayhoff. That is, so this is a board pile. So he proposed actually skin friction is equal to N. So further he said it should be less than 100 kilopascal, And method 2, say if you look at the ICTAD guidelines according to 1997 guidelines, or maybe CEDA guidelines afterwards, it is actually 1.3 times N, right? So that is the in kilopascal, and it should be less than 100 kilopascal, right? So method 3 is actually ICTAD guidelines, again with the critical depth concept. So you have the critical depth and you take it as actually 13 times the file width, right? And Ks is given in the according to that, Ks is equal to K naught. So we say that it is equal to 0.35, right? So that is determined based on the phi value determined from the SPT testing. And method 4 is method 3, same as method 3, but you are using the critical depth from that particular chart which I showed you earlier from the Poulos and Davis, and K's value obtained from the same chart which I showed you, right? So it is method 3 and method 4 are the same, but you are using two different approaches, right? That is what one is method 3 is from the ICTAD and method 4 is from the Poulos and Davis. And method 5 is actually same as method 3, but we are not considering the critical depth concept. We are considering only the variation of the normal variation of the effective overburden pressure, vertical effective overburden pressure with the depth, right? And also we assume that K's value is equal to K naught. K's value is equal to K naught, right? So those are the 5 methods of determination of the skin friction from the soil. And so we use actually 4 methods in estimation of the N bearing, right? So the method 1 is use of the methods as suggested by Poulos and Davis. So there you say that it is CNC plus vertical effective stress multiplied by NQ, right? In this board pile we get the initial phi value minus 3 degrees as the after installation of the pile, that is a phi value. So based on that phi value we determine NC value and NQ value. Of course NQ value and NC value is always equal to about 9 CU, right? NCV is equal to 9, but NQ value we do obtain from this particular relationship, right? That is method 1. And method 2 is the method used in the Bowles textbook, right? So Bowles advocate that we can use the defined in the Bowles textbook, right? So we say that the with the shape modification factor is equal to unity and the normal overburden pressure in the soil, right? So that is Q bar value, right? So that is method 2. So that is as mentioned in Bowles textbook, right? And method 3 is actually based on the ICTAD guidelines, right? So we are using the critical depth concept, and so we are taken as 10 to 15, so about 13 B, the critical depth. And so we are using actually this particular relationship as mentioned in the ICTAD guidelines, right? So that is method 3. And method 4 is actually empirical correlations, kind of, right? So this is specified in the ICTAD guidelines, that is 40 times N. That is the mobilized N bearing capacity, allowable, mobilized N bearing capacity. And also for sandy soils, that is 40 times N. For clay soils, 9 times Cu, right? So for clay soils, 9 times Cu, and for sandy soils, 40 times N. So that is the method 4, fourth method that we use for the estimation of the N bearing capacity, that is given in the ICTAD guidelines. So we will see now, like, what are the methods that will actually closely match with the measured ones, right? For this particular case study. Now, so these are the mobilized skin friction, right? For example, if you take test pile 1, test pile 2, and test pile 3, right? TP1, TP2, TP3 are the 3 test piles, right? So as I mentioned to you earlier, so there are actually 3 strain gauges along the pile along the pile shaft, right? So between strain gauge 1 and strain gauge 2, you can the measured skin friction is for test pile 1. Test pile 1 is this one, right? Test pile 2 is this one, and test pile 3 is the green one, right? Strain gauge 2 and 3, that is the skin friction, mobilized here, are, this is test pile 1, this test pile 2, and this test pile 3, right? And these are actually measured in bearing, right? You can see for test pile 1, it is like this, right? And this is for the test pile 2, right? And this for test pile 3. Now, one thing is that if you look at this one, you can see that the mobilized skin friction values actually taper off. What we assume is correct, maybe, right? So we can get actually it will increase linearly, not linearly, but it will increase up to a limiting value and then will remain constant. So that is shown here also from the measured data. And also the in bearing, you can actually, it will also increase and it will taper off. It will actually taper off, right? The measured values. So now if you compare the ground condition, right? In test pile 1, right? Between strain gauge 1 and strain gauge 2, right? So you have the SPDN value greater than 50. That is so the ground variation here is very limited, right? And you can see the strain gauge 2 and strain gauge 3, the variation of the SPDN value is greater than 50. So in test pile 1, always you get SPD greater than 50. And test pile 2, right? So at the top you get a little bit lower SPDN value, and below that you get a higher SPDN value. But the other thing is that we have a note here is that in here, right? So the toe is actually in the clay soil, right? The second case, toe is in the clay soil, right? But in the third test pile, so along the strain gauge 1 and strain gauge 2, you get 44 SPDN value, and below strain gauge 2 and 3, you get SPD 50, and below that, near the toe, you get always SPD more than 50, right? So those are the three test piles that we consider, right? So now if you predict the the first one, right? So if you look at the first prediction here, right? So if you are considering, for example, now let alone the test pile 1, right? If you look at test pile 2 and test pile 3, right? So this is actually strain gauge 1 and strain gauge 2. So you have actually SPDN value 43 here and 44 here. And so this is actually the difference between the predicted value. So this is actually estimated, the predicted value, right? So this is the measured value, right? So this is the predicted value. Again, test strain gauge 2 and 3, between strain gauge 2 and 3 predicted value, and these are the measured values, right? So you can see in the test pile 2 and test pile 3, between strain gauge 1 and strain gauge 2, right? So you get SPDN value of between with dense material, but it is not very dense, right? So you can see that the method 3, that is basically the ICTAD method, right? Using the critical depth concept and estimated soil strength parameters, right? So that is method 3. So if I go back to method 3 here, right? The skin friction determination. So you use the ICTAD guidelines and critical depth concept as 30 times B and Ks is equal to K0, right? So if you use that the critical depth concept, right? So you can see that the method 3 is giving actually the lower error, right? Coincidentally maybe, right? If you consider this one, the case for the test pile 1, right, where you have actually between strain gauge 2 and 3, SPDN value is more than 50. So that is also giving the the error, error 0, right? So, but that may be a coincidence. We think that because in the other case, for the strain gauge 1 and 2, it is giving a higher error, right? So therefore, what we are saying is we are speculating here that if you consider the dense and dense soil, right, at the ground surface, right, both of these are actually at the ground surface level. So then the ICTAD method 3, right, may be reasonable. That is the conclusion that we get here, right? And so if you look at the very dense material, that is when the SPD value is greater than 50. So in that case, what we can see is the method 2, that is method 2 is actually empirical correlations proposed by ICTAD, right? So it says SPT n value times 1.3 is the mobilized skin friction, right? So that is the method 2, right? So the method 2 will give the lowest error, right? So therefore, what we can say is, we can speculate. Of course, there are only 3 test piles here, right? So based on that, we have reasonable empirical correlation to estimate the skin friction, mobilized skin friction, right? So that is proposed by in the ICTAD, right, guidelines and or CEDA guidelines. So in that case, it is 1.3 times n value. So you can roughly estimate the mobilized the skin friction. Of course, this has gone to the ultimate region, because it is in soil, right? But if it is a dense material, right, especially at the ground surface level, then you can use the critical depth concept and determine the ultimate skin friction value, right? So that is the skin friction comparison. But if you look at the end bearing comparison, right, so it says always method 4. Method 4 is actually the ICTAD method, right, where we can have actually determine even for sand. For sand, we get 40 times n, and for clay we get 9 times Cu. So both these may, for both sand and clay, the ICTAD method actually give the least error, right? So you can see here, like it is almost of course this one is 31, but this is actually over predicting, right? Sorry, under predicting value, right? So because the prediction is actually less than the mobilized, right? So here maybe we can say that we can reasonably estimate the skin friction, the end bearing in soil, right? Mobilized end bearing in soil using the guidelines we have now, right? And even the skin friction we can estimate the using the guideline now, right? What we have, but those are actually not the problem, right? So if you look at actually the rock socket, right? So there I am actually describing some other case studies, not the same case studies, but some other case studies. All are obtained from the from the instrumented pile load testing, right? So now here ultimate skin friction mobilized, right, is actually a limiting value given in the ICTAD guidelines, right? That is 200 kilopascal, and method given in Hong Kong guidelines 0.2 times sigma c to the power 0.5, right? And method given by proposed by William Ittad. So these are the MA1, M1A, M2A, and M3A, and M1B is actually method that is the you compare you estimate the mobilized end bearing and you compare that with the end bearing mobilized, right? So method 1B is actually what is outlined in ICTAD guidelines, and method 2B is basically the chart that we are talking about, and M2B is method given in Hong Kong guidelines that use in the RMR value. You can determine the end bearing, and Method 3B is actually, what is proposed by Kulhar, right? So that is again another method that is proposed by a researcher. So we compare that as well, right? And so this one actually, the elastic modulus of the bedrock, I did not talk about that, but we compare that as well, right? Using the what is given in BS 8.4, we determine and then compare that with the measured value, right? And the method given in the Hong Kong guidelines and method given by the PRA, right? So that is the that is again another empirical method, right? So we will see that now for these instrumental cases, like 3 cases, we determine the RMR, right? So based on the rock cores that were developed, and we approximately determine RMR. So using the rock core, you cannot determine correctly the RMR value, but you can determine the approximate RMR value, right, using the rock cores, right? So if you determine for case 1, it comes to between 52 and 57, right? And case 2, it is actually RMR is less than very small, 25, and case 3 is actually less than 25, indicating that this is highly weak area which is having RQD less than 10 and core recovery is between 30 and 50, right? So for both these case 2 and case 3, right? So now if you compare that, so these are actually some of the graphs, right, for case study 1, that is based on the instrument pilot test. So these are actually the mobilized graph, mobilized pile top force versus pile displacement of displacement. Now this is the graph. You can see that the it is not displaced even more than 7 millimeters, right? Even when you apply the 3 times the working load. Now this is the actually bottom settlement versus mobilized end bearing capacity. You can see the mobilized end bearing capacity is in the range of 6,000, right? At display bottom displacement of about 4 millimeters, right? So this is the mobilized skin friction for case 1 because it is on a fairly solid rock. You can see now it is tapering off maybe, right, but not develop to the ultimate value, so it can increase further, right? So you can see the mobilized value is in the range of about 700 kilopascal, right, at a settlement of about 4 to 5 millimeters, right? So if you compare the estimated ultimate value, right, estimated ultimate skin friction and mobilized skin friction, right? So you can see that using method 1, so method 1A, always you limit to 200, so it will predict 200 here, right? Method 2B, that is the Hong Kong guideline, so if you determine, and method 3A is basically using the Williams method. You can see here, so what we get here is the observed value, right? So you can see that observed value, so this has not come to the ultimate value yet, right? So you can actually mobilize a little bit further. So what is mobilized in case 1 is about 270, 712. Now here 710, what is mobilized, right? So even in the weak conditions, so these two are actually weak rock conditions, you can see that even here, you have mobilized 334 kilopascal, the mobilized value, right? So these are the predicted values from these 3 methods, right? So even for the weak rock conditions, what is given in the CEDA guidelines or the ICTAD guidelines is not 200 is not sufficient. Now that is even for these 3 cases, of course, limiting cases, limited number of test results, but here the values are quite under predicted by the CEDA guidelines. But these may be reasonable, right? and predict the values here. And so if you look at the end bearing capacity, mobilized end bearing capacity, if you are using the method 1, right? So that is the basically what is given in the CEDA guidelines chart, right? You can see that the value here is 4,000, but for the other two cases, the core recovery is very low, so therefore you cannot estimate, right? Now even here you cannot estimate because using the Kulhavi method you cannot estimate because the rock is very weak, right? And RQD is very low, right? But only method that is only one that can be compared is actually the case 1, right? For the case 1, what is predicted here is actually about 4,000 using method 1, and method 2, that is basically from the Hong Kong guidelines, it is giving value in the range of 6,250, and the method 3, right? So the basically the Kulhai method gives very close to this one, something like 2,500, right? But the observed value is about 5,769, and it is increasing. So this is will agree with the Hong Kong guidelines method. And now here, for the case 2, you can see the mobilized value is about 10,000, 10,800 here, right? But these values actually, there are no predictions here. Even for the Hong Kong guidelines, will predict about less than 3,000, right? So what is mobilized here is about 10,800, right? And for the case 3, right? So this is still increasing, and you can see it's about, the prediction is about 3,200, 3,025, but here is allowable capacity is about 3,000, right? So this is further increase at a lower settlement, right? So you can see the comparison here. Of course, the comparison of the these are the comparison of the E values that are determined, right? Using method 1, you can see the predictions, right? Method 2 predictions, method 3 predictions, and method 4 observed values, the E values, right? So of course, you have to mention that 3 case studies are not sufficient to make a conclusion regarding this the skin friction and bearing in the rock. But there are some other case studies which are done afterwards, right? Will actually support the higher skin friction and higher end bearing mobilized in the rock socket, right? So based on this, we can we can come to an agreement or the conclusion based on like 200 kilopascal limit even in the ICTA or CEDA guidelines may not be sufficient, right? The reduction of the mobilized skin friction due to the use of bentonite slurry is not seen here, right? So the bentonite slurry, you can reduce the capacity by 1/4 is not shown here. And method in Hong Kong guidelines and method proposed by William et al. Estimate the ultimate skin friction mobilized in the rock socket seems to be reasonable, right? But of course, we have to have more results to come to the conclusion regarding the rock socket. Now, finally, like if you look at the other test results available, of course, there are some more test results which will support the earlier conclusions, and these are actually test results from the Osterberg load cell test that are done in Sri Lanka, right? So you can see that even this one, these are mobilized the skin friction. So in the Osterberg load cell, of course, they use 2 Osterberg cells here. So basically you get the skin friction here, right? So you can see the skin friction there also is about 7,700 kilopascal, much more than 200 that we are talking about, right? And of course, because of the problem of the skin friction here, you cannot mobilize the full end bearing, right? So the end bearing is also increasing here at even at a very low the displacement values, right? Low displacement, the end bearing values are not fully mobilized, but still you can see it is still increasing. So what we concluded from the rock socket is actually regarding the rock socket is actually maybe partly supported by the findings here. And also the final conclusions regarding this estimation method for soil end bearing capacity and the skin friction capacity may be sufficient, right? So that shows that what we use currently are sufficient, but we have to pay special attention to completely weathered rock and maybe lateritic soils that are found in Sri Lanka, right? So these are actually two exceptions. There may be more, like you have to have test results, but that is reasonably predicted, right? Skin friction and bearing capacities of the socketed portion of the bedrock is not fully understood, right? So we can see that in bearing capacity and the skin friction is actually that is mobilizing the rock socket is not fully understood, and maybe say you can actually optimize the pile design, right, by using some other methods. Of course, you have to back them by the research, and we are in the developing stage, right? So we can do more testing, and then back at that calculation we can optimize the pile design. Of course, we are currently doing that, and when it is accepted, maybe we can use those very high values for the end bearing and skin friction of the rock socket, right? And also we have to look at another thing that we have to look at is whether we are using enough our design method of permissible stress approach is correct. Like if you look at the right around the world, they use the limit state design, right? So in my opinion, say if you are using a limit state design, we can optimize the pile design further, right? So because if you change the design approach like hero code approach and some other method, right, load factor design approach, so in that case we can actually optimize our designs much better, in my opinion, right? Of course, that is not discussed here, but we can maybe we can look into that as well, right? So those are the points that I would like to discuss today. Thank you.
Thank you, Professor Thilakasiri. So it is time for the questions now. There were few questions in the chat box and Q&A. Someone, can you see that? Someone,
Yeah.
can you see that? Or if you, I mean, maybe if you can start with that, you can take whatever.
First one, right?
It's relevant, yeah.
Yeah. First one is the precast concrete driven piles have points tips instead of flat surface for easy driving. Is there a special method of estimating end bearing capacities? Is it acceptable to use projected area? Is there any correction factor to be applied? That is basically we are talking about the most of the driven piles are actually end is tapered, right, for easy driving. So what is asked is actually whether we can use the projected surface area for the design, right, to estimate the end bearing capacity. So that is the usual practice we use, but we did not discuss that today, and we don't have much evidence regarding that, but that is the usual practice, and we use, and we are not using any correction factor as such, right? And we are editing that. Second one, in a situation, second question, in a situation we assume the recommended allowable value are smaller, can we do a PDA and go for a higher value? That is a tricky question, right? Because when you do a PDA testing, right, generally you do one or two tests, and maybe at different locations. So if it depends on the selected location, right? So if you are selecting a weak location, maybe that is correct, reasonable, right? If the assumed value is smaller, and then you can increase it. But therefore, to say that we have to have more investigation points, right? And the bedrock, within that particular area may be reasonably uniform in that case. Otherwise, somebody can say that, at this place where the rock condition is weaker, if you test the pile, you can get a weaker, in a smaller capacity, right? So it depends on the investigation and also, drilling for the piles as well. But you can do that reasonably if in a uniform site. You can increase the value. Am I answering your question, Chaminder?
You can raise hand. Chaminder, who asked the question, can raise hand, and then we can allow you to. Then we can allow you to speak. Otherwise, we'll move to the next question.
Okay. The next question is actually when a pile failed in a pile dynamic period analysis due to soft toe condition, what are the available remedies to accommodate same load bearing? So now regarding that, soft toe, we assume that we did a research, sometimes back, and found that most of the pile failures are not due to design failures, but the construction issues, right? So if you construct the pile and if there are, soft toe condition at the toe of the pile, then the assumed bearing capacity cannot be taken, right? Because that is a construction defect, right? So the remedial action for that is actually provided that you can, using right now, what you can do is what we do is actually we drill boreholes through the piles and penetrate to that particular location, and then flush the soft toe material and then grout that, right? So it depends on the connection between the where you drill the holes, right? So if you can drill the holes and also flush out all the material, then that is the best method that we can rectify the piles, right? So rectification is done usually that way, that normally you wash through one core, and then there should be a connection between first and second core, and then you get the material out from the second core, right? You do reverse that, and then you plug it with concrete. So that you do that, you can rectify that, but provided that, so if it is very very I think if the defect is widespread, right? So under the soft toe condition is everywhere, then you can do that. But of course, it depends on the condition of the weak condition at the rock socket. Am I answering your question?
If you need further clarification, please raise hand, so then we can allow you to speak.
Okay, the next question is for estimation of simplification using Mayhoff method for driven piles, can we use any SPT value encountered? Is there any limitation such as SPT should be less than 50, should be neglected? Can the clay soil layers be considered for simplification capacity? Yeah, any question? Yeah, Loganathan.
I think I have put it to the chat box.
Okay, right.
I think mistakenly I did it.
Okay. So the next question is actually, it says that, when you are using the driven piles for the driven piles SPT count, SPT values, if it is less than 15, whether we have to neglect using the Mayhoff method, and clay soils layers be considered for skin friction capacity, right? So that is a good question, because if you are using the Mayhoff method, right, and for driven piles, not for board piles, right? So that is out of the discussion today. But if you are using the driven piles, using the Mayhoff method for estimating the skin friction capacity, then for clay soils, if you are driving the pile through the soft clay, right? So in that case, actually, you can have negative skin friction. You can, there's a possibility of increase in the pore pressure and generate the negative skin friction. So you have to be a little careful about that. So if you are sure that it is not, mobilizing the negative skin friction, you may use that. But actually, the Mayhoff proposed that method for sandy soils only, right? So for sandy soils, you can use the method that is proposed by Mayhoff. And even if it does not limit the value of SPTN value of 15, right, 1.5, but if you are using 1.5 SPTN value for driven piles, basically you get a about, if you are using a factor of 2, so you are getting about 30 kilopascal, the skin friction capacity ultimate value, right? So the allowable value can be quite smaller. So in that case, you can neglect. But if it is lesser than 15, very small, then you better neglect that, because when you multiply it by a factor of 2, then the capacity you get is very limited, right? So there's a possibility of a negative skin friction also applied.
And there are
Atula, what shall we do?
there are question, no, that there's a lateral. There's talking about lateral load pile.
Which one?
So there is in the chat box. There is one on.
Which one?
I think we have covered all that. No, the last one, there is anonymous. Secondly, what is the point of SPTN correction with the assumed gamma value? Can't we use field N values of estimating and bearing?
Regarding that, generally, like you are talking about the piles in soil, right? Right. So if the piles are in soil, then Mayhoff says that N55 values, right? So it should be multiplied by N55. But if you assume a reasonable value for the unit weight of the material, maybe you can get a fairly accurate value, right? But of course, it is approximate. But because now SPTN values will actually will vary with the depth because of the confinement pressure, right? So therefore, it is always better to use the approximate effective overburden pressure and apply the pressure correction, right, before we use that in the SPT value for to estimate the in bearing of the skin friction.
If there are any further questions, please raise your hand.
Yes, sir, there are a number of participants who have raised hands. You can unmute and you can ask a question, please. Yeah, Jiva, yeah, you can.
Yes, Professor, I would like to ask if we have carried out the IMLT and found out the parameters, friction values and the end bearing values on the IMLT, can we reliably use these values for pile optimization?
That is again.
I have found a situation, soil report, it gives somewhere around 3 MPa for the design. But we have found that it can get go up to 6 lead bearing.
Now, did you do the testing of the IMLT very close to the borehole location?
That's right, sir.
Yeah. So in that case, you may be able to use that, right? But you have to back it up with some other data because this is just one location, right? Maybe the pile hit a good ground condition, like so when you get the drilling record of the pile, that indicates also the weak ground condition, is it?
Yeah, yes, in that case, we have to supervise the piling operation and find the same sample. If we are finding the same sample in each pile, then I think we can use that parameter.
Yeah.
Is it?
Maybe you can use that, but you have to supervise the piling operation very closely.
Very closely.
You are using a value higher than the recommended value.
That's right. Okay, thank you, sir.
Hello, sir.
I can't hear you properly. Can you speak a little louder?
Can you hear me, sir?
Yeah.
Sir, continuing to the software question, sir. I have two questions. One is, what's the minimum diameter of pile we can drilling and do the grouting? And another one is, if when we are doing the pile dynamic test, it's got failed, and if we propose to do some design change and reduce the load, then what's the maximum load? Is it can we derive from the PDA analysis?
Now, if I answer you the second question first, right? So you are asking whether you get a capacity from the PDA test, right? So that is not up to the design value, and it failed. The pile load PDA test failed, right? So can you can you get the design capacity from the PDA testing, right? That's the question, right?
Yes, sir.
I think then you have to see what is the reason for failure, right? So if the reason for the failure is soft toe condition or some unknown factor, then you have to be a little careful, right? Getting a design value from the PD testing. So that may not be applicable at other locations, right? So if it is due to the weak rock condition, of course, you can generally for the end bearing, we get a value of factor of safety of about 3, right? So 3 or 2.5. You can get the allowable end bearing from the PDA test results, but bearing in mind that what is given from the PDA for the end bearing and the skin friction, that separation may not also be correct, 100% accurate, right? So you may have to use a little higher factor of safety against the end bearing predicted by the PDA, and after investigating the reason for the failure. If the reason for the failure is soft toe condition, you have to be careful. The other one is actually what is the minimum diameter you can rectify the pile. So that of course depends on, because now if you look at the drilling a single core, right? If you forget about 2 cores, if you are drilling a single core through the pile, so if the pile diameter is very smaller, even if you drill at the center, there's a possibility that even a slight misalignment with the verticality actually it can go out of the pile, right? So I wouldn't do the correction, the rectification for piles less than about 800 millimeters, right? Using the because there's a possibility that if you drill at the center, then there's about 400 millimeters from one side to one side, right? So then you may be able to drill two cores, right? In that case, if it is 800 millimeter or maybe 1000 millimeter diameter piles, but smaller than that, I don't think that we should do that.
This case, if the pile is less than to 800, then if it failed due to the soft toe, the pile should be neglected, no?
No, I'm not saying that that 800 is a magic number. But what I'm saying is that we have to look at the. You can actually rectify the pile using a single core also, right? So if you drill a single core and using what is called a barrel, which is to clean the hole, right? So if you have lateral holes in the water jet can actually clean the hole properly, then you may be able to do that. But drilling two cores and rectifying the piles, I would not go for pile diameters less than 800 millimeters. Am I answering your question?
Yes, sir. Thank you, sir.
Yeah. I can see Thilakasiri, you have a question?
You can unmute yourself and talk.
Thilakasiri,
Hello.
yeah, go ahead.
This is Shiva.
Oh, okay, sure. Go ahead.
Yeah, just want to ask a question regarding about the soft toe again. Is it possible to come to a conclusion with the PIT whether it's a soft toe or the
PIT actually depends on whether the PIT accuracy depends on whether the wave has actually gone to the pile bottom, right?
Mm-hmm.
So if the soft toe condition is very well seen in the PIT, maybe that is a reason, right? The wave has gone to the bottom of the pile and it has shown a positive reflection from the soft toe, right? So if it is clearly seen, yes, you can, right? But of course, it doesn't say that if the PIT is okay, right? So the one reason could be that the reflection the stress wave that you input may not have gone to the top toe also. That is a reason, right? But using a PIT alone, that is sufficient if you can clearly see that the soft toe condition from the PIT.
Okay, understand.
Mind the yeah.
Sir, now sometimes in our soil investigation reports, they are terminating their testing not at the fresh rock level, sometimes in the weaker levels. But at that point, the RQD value is very low and the bearing capacity recommendation is also very low. But normally at the recommendation section, it's normally mentioned that we have to do the rock socketing till we find the fresh rock. So at the fresh rock level, the rock end bearing value is very good. But at the problem is at the tender stage, we cannot use those values to optimize the design. That's the problem, sir. What
you're saying is that the soil investigation report does not show the the fresh rock, right? But if you go to the fresh rock, you can get a higher capacity.
Yes.
Basically, like, when you look at the recommendation part, right? So the recommendations are given based on the information presented, and also the that are actually that are used to give the recommendations. For example, the allowable end bearing capacity depends on, right now the thinking is that it depends on the RQD and the core recovery and the UCS. Right. So based on that, you will recommend that the end bearing, right? But if you go to the fresh rock, you can get actually a higher bearing capacity, right? So if you do not have actually a code to the fresh rock, then you cannot predict that using from the investigation data as well, right? So in that case, you will not be able to optimize it. But my understand my advice is that in that case, right? So if you can actually do some kind of pilot test at weakest location and show, right? Then you may be able to get a higher capacity, right? So the recommendation is given based on the information made available, and also the currently practiced rules, right? So if you go out of that, right, then you may have to show that, right? Okay, the recommendations, you can get a higher capacity than that, than the recommended value, right? So you may have to do that type of thing. Yeah.
Thank you.
Professor, I would like to add to that question. Is it, if we can do a PDA test and find the bearing values from PDA and identify the sample of the sovereign area, then can we, is it is it reasonable to use that value for the file design?
No, actually, I am.
How reliable PDA is?
Yeah, that is the thing. So separation of the skin friction and end bearing from the PDA is, kind of, I don't know. It is, but of course, the total the load settlement curve from the PDA is fairly good estimation of the static load testing. That is understand. That is, accepted. But separation between the skin friction and end bearing from PDA is somewhat not accepted, right? For example, now the user of the PDA, for example, who does the CAPEP simulation, right? So has a certain freedom to he can intervene and change this the skin friction and end bearing values, right? So there's a possibility of doing that, and the match quality maybe even for that case less than a 5, right? So so there's a but if you match the PDA accurately, you can do that, right? But that's why we do instrumental pilot test. So from the instrumental pilot test, you measure the variation of the skin friction and the end bearing, what is mobilized, right? But PDA is not very accurate when it comes to the separation between the skin friction and bearing.
Yeah. Problem, Professor, PDA cost is much less than carrying out a MLT or IMLT. So we have to, as a consultant, always contractors came and ask for PDA to verify the rock samples. So most of the piling contractors, they like to do PDAs, and they always try to convince the consultant, if they have done a PDA, so this rock has taken the load, then why we can't stop the files at a higher level, or something like that. So that's what the provision was. They don't try to go for an IMLT.
Yeah, of
They
course.
always
I
trying to.
understand the cost concern, cost factor. Like, you know, it can be few millions. Like if you are doing a IMLT, but if you are basing your design on the PDA, the one thing is that you have to do the PDA CapEx simulation very accurately. That is one thing. The other thing is that you have to monitor the pile installation program, quite carefully, right? So you have to look at the existing boreholes and boreholes during the site investigation, and look at the drilling records of each pile, and then decide on the termination level, right?
Yeah,
So if you are doing that, you have to be careful.
Understand.
Right. Anyone else? We can allow a couple of questions before we wind off.
Sir, and Jabbar speaking.
Yeah, Jabbar.
Yes. Go on.
Yeah, when we do the PDA test, let's say the tensile stress in the pile has exceeded the allowable limit of the concrete. Does it mean that pile has failed and we cannot use that pile?
So by how much? For example, now PDA CapEx simulation will give the limit of the what is the tensile stress mobilized, right? Maximum tensile stress mobilized, and also if it what your question is, like, what is the limit, right? Whether if it has increased the limit of the tensile strength of concrete, will there be any can we use the pile, right? That's the question,
Yes.
right?
Yes.
Now in that case, I have to say that now the tensile strength of in the pile comes not only from the for example from the concrete section itself, right? So you get the tensile strength from the steel as well, right? So and so if you are looking at the PDA, right? So where the mobilize, the maximum tensile stress is mobilized, right? So you have to see the section, right? So if that particular section is actually reinforced, then maybe that generally what it says is that tensile strength of concrete generally from the PDA is about 4 megapascal or even less than that, right? So what is the value that you got?
4.5.
4.5. I would say that 4.5. Now, if you are not in, if you have a doubt, you can do a PIT on that and see, like, where you got the maximum tensile stress, and see whether there had been any cracking of the pipe, right? So if the PIT shows a cracking, of course, there's a you cannot use the pipe, that particular pipe. But if the wave has gone to that particular section in the PIT, right, and it doesn't show any cracking, then you may be able to use that. In my view, that 4.5 is maybe a marginal value, I would say.
Thank you.
There is a question here in the chat box saying that I cannot join through audio. My questions are, please explain how to select a suitable location for an instrumented pile load test for the test pile, and how many test piles required for a particular project to optimize the pile length.
That is actually depends on the investigation results, right? So if you want to optimize the pile load, the capacities of the piles, then what I would say is that you will go for the weakest location and show, right? Install the pile, and so there can be a weaker location in the in the site than what is encountered, right? But based on the investigation, that is the weakest location. So you can install the pile and show that you can get the capacity at the weakest location. But if you are doing that, then the pile installation has to be done fairly accurately, so that you have to drill the piles until you get that particular the rock samples, right? The rock samples, right? The rock type from the IMLT location, right? So if you can do that, I would say that you go for the weakest location and install the pile there.
Right, thank you. There is Hasanta Fonseca raising hand.
Yes, sir. Hello, sir.
Yes.
Can you hear me?
Yeah, yes.
Sir, in your study, you mentioned that the effect of bentonite has not considered for the study. But my question is, in the reality, can we ignore the effect of bentonite for real case of piling? Because when we are doing the estimation of ultimate capacity, the effect of bentonite is need to be neglected, though it had to be considered during the ultimate assessment.
Now the effect of the bentonite comes from the bentonite cake, right?
Yes.
So if you leave the pile bow with bentonite for a long time, and then there can be a thicker bentonite cake form, and during the concreting that will not be removed. So right, so it depends on the time of the bentonite left in the hole, right? Without, and also how you concrete, right? So if you do not leave bentonite in the hole for a long period, and there's no evidence of forming the bentonite cake for a reasonable thickness, which cannot be removed from the concreting, right? So you have to see that how long that the bentonite is left in the hole, and then what is the thickness of the bentonite cake, and how strong that particular bentonite cake that is formed around the sides, right? So if it is very thick, maybe, and you have left a very long time, then you may have to consider that. But generally, if it is concreted quite soon, without leaving the bentonite for a long time, then what I said may be correct, right? So, but you may have to adjust it if the bentonite is left for a long time.
So, but when we do estimation of final capacity, is that to neglect that part? If we, as you said, if we doing the proper cleaning and no reasonable time is left without completing.
Yeah, I think so. Because now the test results do not show that effect of bentonite if it is done properly.
Okay.
Right. So if it is done not, if there are exceptional cases, you may have to consider the effect of the bentonite. Okay. According to the test results shown so far.
Okay. Thank you.
Thank you. Yeah. So shall we conclude now? There aren't any more.
There are two raised hands by Access Gavin, right?
Yeah, Professor, can you hear me?
There's Access
Yeah.
Gavin. Yeah, yes.
Yep. I have small question regarding the pile rectification using the grouting. So when there is a situation like that, when we are finding the anomaly in between the pile, in the middle of the pile, let's say around 10 meters from ground level, and it is not reaching to the rock level also. It is in between the pile, in mid of the pile. So then the other thing is, when we have found out that the particular anomaly is also exposed to the outside also, then when we are doing the grouting using the core drilling, then when the grout volume is substantially increasing comparing with the theoretical value, and that particular location is also come up with the peaty soil, so what are the alternatives that we can go rather than going for a alternative pile? Like we are doing the grouting, but it is not finishing it. Still, we do need to have more volume to grout, because that grouting is going away. So
Yeah, I understand that.
Yeah.
because now the the pressure to build up within the pile, right? The ground pressure to build up, then we need to have a confined environment. So right now, what you are saying is that it is in the soil and also exposed to the outside environment, right? So therefore, the ground may be flowing without building the pressure, right?
Yes, Professor.
So,
Yes, using that sonic logging test and the tomography, it shows that it is exposed into the outside. Then when we are going for a grouting, it is not finishing. Still, the volume is going on. So I just need to find out what is the extreme limit of that particular work. Yeah.
now, what we generally say is that you can determine the effective area, right, of the pile using if you have done the sonic logging testing, if I may be correct, right? So in that
Yes.
case, you can actually do a tomographic analysis and see what is the effective area of the pile if you keep a velocity limit of about 3,500 meters per second, right? What is the area that is effective area of the pile at that particular defective section, right? If the area is less than about 80%, I don't think that is you have any other option than having the having alternative piles, right? So better to do a tomographic analysis and see what is the area reduction due to the defect. And the other thing is that you can always say that the area ratio is less than about defective is less than about 80%, right? More than 80%, but still if the reinforcements are exposed to the corroding environment, and if it is especially at the top of the pile, so then there can be some moments applied, and the corrosion of the reinforcement can have a detrimental effect, right? So you may have to look at that whether the pile is subjected to the moments, right? And if it is the case, then the reinforcement corrosion can be quite an issue, even if you have a area replacement, beta value of more than 80% at the defective section.
Yes, Professor. Thank you very much.
There is Lionel Gunavikrama raising hand. Are you there? Lionel Gunavikrama, and then
yes, sir. Yes, sir. Actually, I put in the chat box. I clear me, sir.
Yes, we can hear you.
Hello, sir. Sometimes structural engineer use pile capacity as test results, say exam PD or MLT, but the value is higher than the given the initial listed by the geologist. In the case of legal situation, which one is correct, the test results or any geological recommendation? Or are we going to get again the recommendation after testing?
Now,
hello.
Yeah, I can hear you. Yeah. Now the question of, as I understand, is that you have tested the pile, right? At the location the recommendation was given, right?
Yes, correct.
So then the recommendation,
yes,
test value is higher than the recommended value, right?
Yes, correct.
Right. So the problem is that as I mentioned earlier, that recommendation may be given based on what is presented and what is the current status of the knowledge. So maybe now you have to look at that. Sometimes for example, that the recommender might know that you can mobilize a higher capacity than what is recommended, but based on the current practices that is used, you cannot recommend that, right? So then better to get the view of the recommender again, and see whether that he is agreeing with the results, right? Because now you have to generalize the test results to the entire site, not just one pile location, right?
Right.
Right. So you have to see whether that is that is accepted by the recommender. Maybe there's a case. Yes.
Okay, thank you, sir. This is the real case what I am facing now. That is, okay, thank you, sir. Your answer.
Then Engineer Sharaf. Engineer Sharaf, raising hand. Are you there?
Yeah, I'm there, sir. Hello.
Yeah.
Yes.
Yes.
Yeah, hello, sir. Can I ask, sir?
Yeah. Go ahead.
I have the doubt, sir. Normally, for the rock socket length is increased due to the higher lateral load capacity. So, what are the possibilities for optimizing the socket length in these situations? But as I think lateral load tests are performed in Sri Lanka, is very, very rare for the major projects.
Now when we talk about the rock socket, generally the rock socket is at a fairly deep level, right?
Yeah.
So what are the probabilities? What is the probability of getting the lateral loads to the rock socket that we have to see, right?
Yeah.
So it depends on the depth of the pile as well.
Yeah.
Right. So if it is a deep pile through the good ground condition, of course the lateral load will not be felt at the will not be transferred to the rock socket as such. Huh?
Yeah, yes, some of the conditions design reports I have seen that they have checked for the three checks. One is the axial and the lateral load, lateral capacity, and another one is the fracture, joint fracture checking. So for the answer, for normally for the axial load, it's 3.5 to 4 meters is enough for carrying that one. But due to the lateral load, it will we have to socket like a 6 or 7 meter like that, nearly 1.5 times of the axial socket. So axial load socket. So can we optimize this one also?
Now in some of the highway projects, what I have seen is that you have to due to the structural considerations, you cannot have a short socket, short length pile, right? So the pile length minimum should be like 8 meters or something, right? So that is the requirement of the structural requirement. But other than that, maybe that it is case dependent as well, right? Depending on the case, we have to analyze the case and see like what type of lateral loads that are transmitted to the bedrock. If it is a long pile, especially, but if it is for a short pile, the lateral loads can actually, if the piles are subject to lateral loads, and there's a minimum pile length that they specify, and then you have to even though that the pile vertical capacity and the all the capacities are satisfied, because of the some structural consideration, you may have to socket the pile to the minimum depth. I think, yeah.
Okay, sir. Okay, sir. Thank you. So, answer. Are there any tests for the lateral capacity checking, sir? Like for the axial capacity, we have some tests now, sir. Like that for the lateral capacity checking, are there any tests?
Yeah. Actually, in Sri Lanka also, we do some lateral load testing, and so you can apply the lateral loads to the pile, right, and measure the lateral deflection. So there are tests that can be done, right, and so if you look at the dynamic testing, you can do what is called statognomic testing, or through that also you can apply the lateral loads. But in Sri Lanka we apply the static lateral loads, right, on the piles and measure the lateral deflection. That has been done actually. You can do.
Okay, sir. Okay. Thank you.
Thank you. So then there are no more raised hands as I see. So then shall we conclude?
Yeah.
Right? So on that's a fairly long time. It's almost 8 o'clock, 8:05. Right. So on behalf of the Sri Lankan Geotechnical Society, I wish to express my sincere gratitude to Prof. Thilakasiri for very informative and comprehensive discussion on the presentation on this optimization of the design of rock socketed piles. So we had more than 250 participants throughout the presentation, and a lot of questions were raised by the participants. So which is a very positive sign that they are interested and they were benefited by the presentation. So thank you very much, Professor Thilakasiri, for your efforts. So it is, I mean, just put into very good use, and many people were benefited by that. So I wish to thank all the participants also for keeping their interest and engage in a good discussion. Thank you very much and good night.
Thank you very much.